Welcome to the second complex webinar for the year. Today I'm going to be talking about intermediate Linux topics. So let me just go ahead and share my presentation. Okay, and Cindy, can you just confirm that we are seeing the slides?
Yes.
Okay, perfect. Great. So my name is Bob Sinkovits. I am the former PI for the Complex project. I had retired recently from SCSC. But I'm going to be continuing to have some involvement in the project. So today we're going to be discussing intermediate Linux. We have the slides available here at the bit.ly link, bit.ly/complex. And we have some exercises that you can do on your own here in our GitHub repo. So just a little bit of background about Complex. We are supported by the National Science Foundation. Complex stands for Comprehensive Learning for End Users to Effectively Utilize Cyber Infrastructure. I say it's a new SCSC program. I should update this. We've been doing these webinars for about a year now. But the goal of Complex is to cover the non-programming skills that we think you need in order to effectively use supercomputers. So topics are going to include parallel computing concepts, Linux tools, bash scripting, security, batch computing, how to get help, data management, and interactive computing. So an outline of what we're going to cover today, we're going to start off with an introduction, a little bit of background, why you may find this material useful, who the target audience is. We're going to look at symbolic links. Then going to talk about redirection and pipes, wildcards and globbing, aliases, command history, navigating between directories using pushd and popd, environment variables, the configuration files, pseudo file systems, and Linux quotes. And then we have a little bit of supplementary material at the end in case we have some time remaining. Cindy mentioned questions earlier. Feel free at any time to post your questions into the chat. I have a couple of my SCSC colleagues here who can help answer the questions along the way. At the end, we are going to have a discussion period. We'll be turning off the recording, ask folks to unmute, to turn on their cameras at that time if they like. But we'll see what we could do along the way to answer the questions. All right, so a little bit of introduction and background. I'm going to say that this session is for anyone who works in the Linux environment and wants to acquire additional skills to more effectively use advanced cyber infrastructure. So we're calling this session Intermediate Linux, but in the Linux world, intermediate is all in the eye of the beholder. So everything that we're covering in this session, I think, would be considered very basic or elementary by Linux systems administrators. But I'm going to guess that if you're attending this session, that you're probably not a sysadmin. Rather, it's more likely that you're a student, an educator, or researcher who uses advanced CI as part of your work or your studies. In which case, I'm going to say these topics really are intermediate in the context of Linux users instead of Linux professionals. Now, if you had been attending the Complex webinars last year, you might recall that we had intermediate Linux and shell scripting done as a single session, but now we decided to take shell scripting, split that out into a separate webinar so that we can focus more deeply on the intermediate topics and also do a proper treatment of shell scripting. When we presented this last year, we found that we would get to the point where we had about 5 or 10 minutes left and a lot of shell scripting topics covered, and that's really not an adequate amount of time. So if you look at the Complex schedule, and I forget the exact dates, but coming up we will have a shell scripting webinar. So prerequisites for today's session. First of all, we're going to assume that you already know the fundamentals, the basics of Linux, such as listing files, removing files, navigating directories, listing file content, say using cat and maybe head, tail, less, and more. that you can use one or more of the standard editors like VI, Vim, Emacs, or Nano, and that you understand relative and absolute paths. Now, in the event that you do not already know this material, I do encourage you to stick around. You might have a little bit of a hard time following some of the examples, but you can always go back, refresh yourself in these topics, and then revisit our material. So we're going to start off with symbolic links. So symbolic links, these are also known as soft links. They give you a way to refer to a file by a different name. So they're very useful when you want to avoid writing out a full or a relative path name every time, or if you say have a generic executable name that you want to refer to rather than a specific version. And I'll show in a couple of slides how this could be very useful. Now, to create a symbolic link, we're going to use the ln command with the -s option. Without the -s, you're going to end up creating a hard link, and we're going to talk about this in the supplementary material. Hard links are also useful, but you're going to find that overwhelmingly, you're going to be using symbolic links. To be honest, I have never had an instance in my career where I've had to use hard links, but there are a few times when they do come in handy. So if we want to create a soft link, another way to refer to a file by a different name, we're going to use ln-s, the name of the file that we want to link to, and then the name of the symbolic link. So in the next couple of slides, we're going to explore some of the useful properties of the symbolic links. So first of all, symbolic links can be created even if the file being linked to does not yet exist. You might be wondering, why would I want to do this? Again, I'll show this in the next slide or two, but it is a very, very useful feature. So let's say we go into a directory, we execute ls, and we see that it contains a single file called file1. And now I'm going to go ahead and set up a couple of soft links. I'm going to do ln-s file1, and then a symbolic link to that file called file1-soft. So this is going to be a soft link to an existing file. Then we're going to create another one, but to a file that doesn't yet exist. ln-s file2, file2.soft. So now if we look at the contents of file1, we could do cat file1, we see contents are contents of file1. If we look at the contents, instead referring to the soft link, file1-soft, we again see that content. Here, think of file1-soft as just being another name for file1. Okay, so let's look at what's going on with that second symbolic link. We do a cat file2-soft, and we get the message, no such file or directory. But now we're going to go ahead and create that file. We'll do echo, and then quotes, contents of file2, redirect that into file2. Now, when we look at the contents, in this case referring to the soft link, cat file2-soft, we will see the contents. When we remove a symbolic link, it does not affect the original file. So again, let's look at the contents of our directory. We have file1 and file2, and then we have our two soft links, file1-soft, file2-soft. We can go ahead and remove those soft links, and we'll see that our original files were not affected. A file can have multiple symbolic links. So again, we're going to look at our directory, assume that we just have a single file, file1, and now we're going to create three separate symbolic links, all pointing to file1, file1-soft, file soft1, file1-soft2, and file1-soft3. And if we look at the contents of that directory, we will see the original file and all three soft links. Symbolic links can point to directories or files in other directories using absolute or relative paths, and they can even span file systems. This is one of the really important features of the symbolic links that you're not going to get with a hard link. So let's say I go into my home directory, and now I'm going to create a symbolic link to a file that's in our Expanse in our Expanse Luster file system. So I'm going to look at the file Expanse, Luster, Scratch, Sinkovit, file 4, and I'm going to create a soft link, file 4-soft. So the Expanse, Luster, Scratch, that is a separate file system, but I was still able to create those symbolic links. Now, how do I know if a file is a regular file or if it's a symbolic link? If I do ls-F, it's going to append an @ sign to the file name. If I do an ls-L, it's going to show an L in the first column of the output and list the file that it points to. And there's a third option. And I know that one of our sysadmins who's in attendance is probably going to groan that I even included this, and I'll tell you why not to do this. But if I do an ls --color equals auto, that's going to display the name in teal. But what this does though is it adds overhead to the file system operations, and this is going to be especially critical if we are looking at the contents of directories containing large numbers of files in one of the Luster parallel file systems. So I'm going to encourage you to just use these first two techniques. So we see the output below. I do an ls-F. I see file 1, file 1-soft has the @ sign at the end to indicate that is a symbolic link, and similarly for file 2-soft. If I do an ls-L, I will see that these two symbolic links, they are indicated as being symbolic links with that L in the first column. And then in the last column output, you'll see the file that the symbolic link points to. So where are these going to be really useful? So let's say we have an application, an executable that has multiple versions, and although we occasionally need to access earlier versions, let's say we normally want to access the latest release. So by creating a symbolic link to this most recent version, we can avoid having to update our job scripts or workflows just by updating the link. So, and also assume our application takes multiple input files. While one of these files is different for each calculation, others refer to reference data that rarely changes. So here we can create a symbolic link that points to the latest reference file. So let's say that I have an application. I'm looking in my home directory, home application/bin, and I do an ls. And let's say I have 3 versions of an executable file. This is, let's say, a CFD application. And we label them _v 1.1, 1.2, and 1.3. I could also create a symbolic link now, link ln-s, looking at a symbolic link that's going to point to version 1.3.exe, and I'll call this symbolic link cfd app.exe. So now, if I go ahead and I create additional versions of this executable, and I always want to be pointing to the last version, I do not need to go into all of my scripts and manually update, say, version 1.3 to version 1.4, 1.5, and so on. I could have this symbolic link, which I'm going to update so that it's always going to point to, say, the most recent version of the executable. Now, let's say we also have reference data that we need to work with, and we have multiple versions of reference data. Version 1.1, 1.2, and 1.3. Here, again, I could do the same thing. I could create that symbolic link and have it point to a particular version of the data. And now, if I want to, assume that I'm always going to be working with the latest version of the data, I could just go ahead and update that symbolic link. Now, let's say we have a job script where we're going to execute this CFD application. Here, notice that I have in bold, I have cfd app.exe. I did not specify a particular version. I'm just using the symbolic link, which I assume is always going to be pointing to the latest version. And same thing with the reference data. I didn't have to refer to a particular version of the reference data. I just used the symbolic link, ref.dat, And behind the scenes, I'm going to always keep that updated to point to the next version. So this makes it much more convenient. But notice though that I don't need to use a symbolic link if I ever wanted to go back to another version, say, assuming that I didn't want to make my default the latest version, I could have specifically referred to, say, version 1.1, 1.2, and so on. Okay, so moving on to redirection and pipes. And this is a topic that I assume that most of you are going to be at least a little familiar with, but I'm going to point out a few nuances. So most Linux commands write to standard output, which is the terminal if you're working on the command line. Output can also be directed to file using the greater than symbol. And if we use two greater than symbols, this appends output to a file. So let's look at an example. Let's say I'm going to run the date command. So I'm going to execute date. I'm going to redirect the output into a file called outfile. And if I look at the contents, I see here Tuesday, June 28th. And we see the timestamp, 15/31/20, 2022. Now, if I execute that same command again, it's going to overwrite the content of the file. But instead, if I use two of the greater than symbols, date greater than out file, if I look at the content, I'm going to see that I've now appended the output. And I should point out that you can use you could use appending even if the file doesn't already exist. So you don't need to add logic, say, into your scripts to determine if the file is empty. If you're over the course of, say, a series of calculations, you can always have the first output appended to a non-existent file. Now, pipes take the standard output from one command and it directs it to the standard input of a second command. An arbitrary number of commands can be connected using pipes. So let's say I wanted to count the number of files in the current directory. I could do an ls-1, and then I can pipe that into wc-l. wc is a word count utility. -l says, give me the number of lines. And we can see that we have 13 files in that directory. And I know that there are other ways that you could probably do this, but I find this very, very easy and convenient. Let's say we wanted to list the 3 longest running jobs on a particular compute node of the Expanse supercomputer. Let's say in this case, exp-2-09. Here I could execute the sq command. I could pipe that into grep exp-2-09, and then I can pipe that in head to look at the 3 longest running jobs. Again, I know there are other options that we could use with sq so that we refer to a particular node, but I just wanted to illustrate how we could pipe multiple commands together. So standard input can also be directed. This is something that you might not do quite as often, but it is very useful in some cases. So let's say that you wanted to prevent a command from listing the name of the input file. In the example below, we avoid having to pipe the output from wc into the cut utility. So let's say we do a wc-l, file1.txt, and we see that file1.txt contains 9 lines. Now, we could have used the Linux cut command. So we take the output of wc-l, we use cut so that we extract just the first element, the first field in that record. So now we get line count. But another way we could have done this, and much more convenient, is we do wc-l, and now we use input redirection, $sign, file1.txt, and here we see that we get just the line count. All right, so we're going to move on to wildcards and globbing. So wildcards let you express a pattern for matching multiple file names using any combination of the following, where a question mark matches any single character, the asterisk matches any string, including empty strings, and a list of characters or a range of characters in square brackets allows us to match multiple characters or a range of characters. So globbing is just the operation that expands the pattern into a list of files. So globbing is done automatically by many Linux utilities that operate in files, and these utilities would include ls, rm, mv, cat, head, tail, and the file command. So now we're going to look at a couple of examples. So let's say we have a directory. We have some, what is that, about 20 files in there. Names such as abcde.txt, axcde.exe, and so on. And let's say that I want to list just particular files, say where the file names follow certain patterns. So if I do an ls file star, this is going to give us all of the file names that begin with the string file, followed by any characters. So here we'll see file1.dat, file2.dat, and so on. Now let's say I just wanted to list files that begin with the letter F. Here I could do ls f star, and I'll see fgij.txt, file1.dat, and so on. And then let's say we want to look at all of the files where the file name contains the string ghi. Here I could do ls asterisk ghi asterisk. So this is going to be really, really convenient when you're working with large numbers of files. You want to filter them. Let's say you want to sort them into different directories, maybe based on timestamps or prefixes or so on. This gives you a lot of power. One of the important things to note here is that we can use more than one wildcard. In that last example, we actually used 2 wildcards. We can also do globbing using the question mark. Recall that this matches any single character. So we're going to start off, we're going to list the contents of our directory. We're going to do an ls file .dat. So what this is going to give us is a list of any files with the name file, followed by any single character, followed by the string .dat. And here we'll see file1, file2, etc. .dat. We could mix the question marks with the asterisks. So here we're going to do something a little more complicated in the third example. Here we're going to list all files that start with the letter A, followed by any single character, followed by cde dot, followed by any string. And here we get abcde.txt, axcde.txt. And then finally, the last example, we want to list any files that are any 5 characters, followed by dot, followed by any character, an X, and any character. And here we can see the output. Finally, we can do wildcards and globbing using square braces. So here we start off by listing the files. We do an ls file, and then in square braces, 1.3.dat. So this is going to list any files of the format file, followed by the number 1 or the number 3, .dat. Now notice in the next example, if we use a dash between those numbers, now we're specifying a range of integers. So in this case, ls file and in square braces 1-3.dat. It lists file1.dat, file2.dat, and file3. We could also do matches looking at a list of letters, here in square braces AC, or we can look at ranges of letters, in this case A through C. Right, so let me just check real quick, see if there are any questions in the chat. And I am not seeing any, so let me... Oh, I'm sorry, I do see... Okay, I see a note from Winston. And Trevor, thank you for answering the question about the symbolic links. Okay, so I'm going to go back. Continue with the presentation. Okay, so next we're going to look at aliases. So aliases, all they are is a shortcut for a Linux command. So these are useful for keeping you out of trouble, say accidentally deleting all of your files, and for abbreviating complex commands. So the classic example of defining an alias that's going to keep you out of trouble is if we alias rm, remove command, to instead be rm-i. What this is going to do, it's going to force rm to ask you about each file that you want to remove. Sometimes you might say want to remove files that end with the extension, say, .exe. You do an rm space star.exe. But if you accidentally had a space between the star and .exe, it would be interpreted as rm asterisk, which matches all files, and then .exe. So, we really suggest that you alias rm to rm-i. And now, if I use the which command, I can see that rm is alias to rm-i, and the user bin rm also tells us that we are using the rm command installed in the user bin directory. So this is one that I recommend everybody puts in their profiles. I also find aliases really useful for abbreviating long commands. So below I show one that I use frequently. I want to get a listing of all of the slurm partitions, but I want to format this in a particular way that makes it easier for me to read. So here I said alias partitions, and then I set it equal to sinfo-o, and then a long string that specifies the output format. It took me a while to get this output format just right, so that each of the columns have the right width, that I'm getting the right fields and so on. And I don't want to have to remember this. I don't want to have to recreate this later. So by creating this partition, I can now use this instead of retyping that complex command each time. Now, if you want to see a list of all of your aliases, just execute alias from the command line without any arguments, and it will list all of your aliases. So you can see that I have an alias for listing the slurm partitions, another one for slurm reservations. I've an alias removed to be remove-i, and so on. And then I had a few aliases for getting an interactive node or one core on an interactive node on Expanse. Command history. So the history command lists all of your previously executed commands. So let me back up. Not all, but it's going to be a very long history. I believe by default it might be the last 500 commands, which I think is plenty for most people. You could modify that by setting different environment variables, but let's assume that we're just going to go with the default. So I'm going to start off, just see what happens when I execute history. And here, the snip indicates that I'm not showing all of the output. I didn't want to show 430 lines of output. But you could see, here, I'm showing at the bottom here, the last 3 commands that I've executed. Echo hello, I removed a particular file, I executed ls to list all of the files of the format, file star.txt. Now there are also special commands to execute previous commands. One of the most useful ones is just bang bang, 2 exclamation points. That's going to execute last command. Another way you could have done that was navigating through your history with the up and down arrows. If you hit the up arrow once, you'll get the previous command. You could also execute the last command that started with a particular string. So if we look at the example over here on the right, I have bang ls, and that's going to execute the last ls command, ls file star.txt. And let me just see in the chat. Oh, good. Thank you, Nicole, for following up on the symbolic link question. We can also execute a specific command from the history. We can refer to them by number. So let's say I wanted to execute command number 428. If we look over here in the upper left, that was ls file star-text, and I could just do bang 428 and execute that command. Okay, we're going to move on now to navigating between directories with pushd and popd. So I'm going to start off with an example that's very abstract, and then we're going to look at something a little more practical. So pushd is going to push a directory onto a stack. Popd is going to remove the top directory on the stack, and dirs, D-I-R-S, is going to list the current contents of the stack. So you might be wondering, why am I going to do this? We'll get to that in the next slide. So let's say we start off, we do pushd, dir1. We see now that directory 1 has been pushed to the top of the stack, and just below that is directory ppdem. Now we can push another directory onto the stack. You can see in the second output that we have 3 directories on the stack. If I do pushd without any arguments, it's going to swap the 2 on the top. If I do pushd plus followed by a number, it's going to take that directory on the stack, move it to the top. I could do dirs just to list the directories on the stack, popd to pop the top one off, and popd plus a number to pop off a particular directory. Again, they're very abstract, but I'll show a very concrete example where this is going to come in handy. And this is something that I do all the time. Let's say I'm developing an application and I'm modifying the code and I'm testing the code. And I'm going through this very tight cycle of modification and testing. So to keep our work organized, I like to do the code development and the execution in 2 separate directories. Pushd and popd allows me to easily move between the 2. So let's say that I'm in a directory. I'm going to call it code-dir, and I'm going to do some work in this directory. I'm going to edit the code, I'm going to build my executable. Then I'm going to do pushd, and I'm going to move into the run directory. And here's where I'm going to run the code and examine the output. If I execute the dirs command, I see that I have run dir and code dir on the stack. Now, I want to go back to editing my code and building my executable. I do pushd, it's going to swap those 2 directories on the stack. I'm all done doing my editing and building. Do pushd again, swaps the top 2 on the stack, and I'm now in the directory where I'm running the code. So really, really handy if you find yourself doing something where you're moving back and forth between 2 or more directories. I find that sometimes it's convenient to have an extensive stack of directories, but most often I will find that just a couple of directories, in this case, one where I'm editing and building the executable, another one where I'm running the code and examining the output, is sufficient. Let me just take a look at the chat. So I see a comment here from Armel. It says me too. Is this a question related to the usefulness of symbolic links? Okay, well, I'm going to move on. I'll let my SCSC colleagues answer that if you have any further questions. All right, so now we're going to look at environment variables. So we have shell variables and environment variables, and these allow you to customize your environment and control how applications behave on a Linux system. So shell variables are only known within the current shell. Environment variables are known globally and inherited by processes and shells that are launched by the current shell. You're generally going to want to use environment variables than shell variables, and I'll show you a few examples in the next couple of slides. Shell variables are set Using the key equals value syntax, space is not allowed around the equal sign, and by convention, the key is going to be capitalized. Shell variables are made into environment variables using the export command, and the value of a shell or an environment variable is accessed using $key. So an example of an environment variable that you probably use all the time is home and user. So for example, if I just type $home or $user, where the name is in all caps on the command line, I'm going to see my username or the name of my home directory. But let's look at a few examples of setting these shell and environment variables. So let's say I have two variables. I'm going to call them key1 and key2, and I'm going to set them to these strings, ABCD, EFGH. Now I'm going to use export key2 to make key2 an environment variable. Again, this is what you're normally going to want to do. But even better, instead of doing this on two separate lines, I could define a variable and make an environment variable all on one fell swoop by doing export, in this case key3, and equals the string ijkl. So now if we do an echo $key1, $key2, $key3, we can see what the values are. ABCD, EFGH, IJKL. Now here's where the difference between shell and environment variables comes in. Recall that key1 and key3 are environment variables. They are going to be inherited by new shells, whereas key1 is just a shell variable. So let's say that I create, that I launch a new shell with /bin/bash. I do an echo $key1. I'm going to get empty output. Key1 was only known in the present shell. Whereas if I look at key2 or key3, I will see the values that were assigned. Now, this may seem a little abstract. You might be wondering if I'm working at the terminal, maybe I'm not going to create a new shell very often. But where this is going to be important is if you are launching batch jobs and you want any variables that you define to be inherited when that job is executed. Now, another way to declare the shell and environment variables, and this is I see being used more and more frequently, is to use the declare command. If we use -x, that's going to export it, essentially make it an environment variable, and -r if we want to make that variable read-only. So here we're going to declare a shell variable, declare var1 equals abc. Next line, we're going to declare an environment variable, declare -x, var2 equals def. We could see that within the shell that we have access to the values that had been assigned. But if I create a new shell, like I did in the previous slide, since var1 was the shell variable, it's not going to be known by the child shell. So again, you're overwhelmingly going to be using environment variables, either with the export command or declare -x. Now, if you want to get a listing of all of your environment variables, just use the env command, and I'm showing here a partial output. So I do env, I could see my path. This is a set of paths that are going to be searched for files, library path, man path. This is where user man pages are located. I see my log name, my shell, my home directory, and so on. All right, so now we're going to move on to configuration files. So Linux has a number of configuration files for customizing your environment. We talked about creating aliases, setting environment variables. You don't want to have to do that each time you log in. It would be nice to have those saved for you so that when you do log in, they're already available. So we can edit various configuration files so that our environment variables or aliases and functions and so on are saved. Now, to make things A little confusing is there's a hierarchy of scripts that I'll be showing in the next few slides. Scripts can execute or source other scripts, and some scripts only apply to login shells. Fortunately, you can usually get by, for regular users, again, as opposed to sysadmins, with just two general rules. I'm going to say customize your environment variables in your .bash underscore profile file, and put your aliases and any functions you define in your .bashrc. So before we get into the specifics, we're just going to talk about interactive login, interactive non-login, and non-interactive shells. So an interactive shell is one that reads from and writes to the user's terminal. This is probably what you're most familiar with. So if you can enter commands at the command line and see the output, you're in an interactive shell. So let's say you log into the Expanse login node, you start typing commands, you're working with an interactive shell. An interactive login shell is one that you launched using SSH, locally or when a new shell is launched with the login option. Again, this is where you'll usually work. An interactive non-login shell is launched from a shell by executing bash at the command or open a new terminal from Linux desktop. Now, a non-interactive shell is not associated with the terminal. This is usually launched by a process, usually launched by a user executing a script or associated with an automated process. So there's going to be an order of execution of these configuration files. I'm showing the ones that are controlled by the sysadmins in orange, and the ones that you own or have control over in blue. So the ones you're really going to be concerned with, again, are the .bash underscore profile and the .bashrc. But there's going to be a hierarchy of scripts that are executed. The sysadmins are going to be putting a lot of stuff into etc profile, etc bashrc, and various directories in the etc profile directory. If you're in a non-interactive login shell, everything's going to be controlled by .bashrc and etc bashrc. Now, if you do an internet search for Linux configuration files, you might come across figures that look like the following. Kind of ugly, kind of overwhelming. There's a whole series of shells that are calling other shells. There's, in some cases, multiple dependencies. But the good news is, if you're using bash and you're not a sysadmin, you probably just need to worry about two files. Again, the .bash underscore profile and the .bashrc. And give me just a sec, I saw I believe that we had a comment. Oh, great. Thank you, Trevor, for the follow-up. All right, let me get back to the presentation. Okay, so what's going to go into your .bash profile? This file, when we create an account for you, or whenever any sysadmin creates an account for you, this is going to be in your home directory. Since it begins with the dot, it's what we call a hidden file. You're only going to see it if you do an ls with the -a option. So use your .bash underscore profile for commands that should only be run once, such as customizing environment variables. Now, if you open this file, you will see some content at the top. See, in particular, these three lines here, if -f tilde.bashrc, then execute .bashrc. Do not edit this part. This is boilerplate that you do not want to tinker with. But down below that is where you can specify your environment and your and things that you want to do on startup. So here we might be defining our path. So we're appending our home directory .local bin, home bin to the path directory. I have a path to my Anaconda installation. I have a path to the AMD uprof tool, and then I export the path. In the .bashrc, this is where we're going to put commands that should be run for every new shell. Again, there's going to be some boilerplate at the top. You can see here that we would be executing the contents of the sysadmin owned etc bashrc. And then below that is where you could to do your customizations. So you could create your aliases. I realize I have a typo here. There should be an alias instead in front of reservations. I'll fix that shortly. You can load some modules. Now we know when you talk to our user services folks, they'll tell you maybe not to not to load your modules in the .bashrc, but I find that it's convenient to load at least the slurm module. And then finally, pseudo file systems. So in the Linux world, everything is a file, whether it's a directory, a device, a regular file, a symbolic link. Linux also provides what we call pseudo file systems that allow you to access dynamically generated content using the same tools that you use to access regular files. These are going to be found in the /proc and /sys directories. As a regular user, you'll probably use these to get hardware information. So let's say I go to the top of the tree, I go to /proc, and I do ls-l CPU info, uptime version. So here we will see that we have two files here called CPU info and version. They have 0 size. But if we either edit this file, sorry, not edit, you're not going to be allowed to edit it. If we output the contents of these files, or let's say we, in this case, that we cat the content through a character count, wc-c, we could see that they are not empty. So these are pseudo files. They give you access to machine information, to processes, and so on. But again, they are not real files. So ls-cpu command interrogates the contents of /proc/cpu info, and it organizes result in a very readable form. So I'm going to highlight some of that output. So let's say we want to know a little bit about the kind of node that we're running on. Now highlighted here in red, we see the architecture is an x86. The total number of CPU cores is 128. We have 1 thread per core, 64 cores per socket, 2 sockets per node. What this is telling, look here at the model name, AMD EPYC 7742. We could Google that and see that it's an AMD ROM processor. So this is really useful information. We're able to tell that we're running on an x86 architecture with 2 64-core AMD EPYC processors, hardware multi-threading is turned off, and the CPUs are organized into 8 NUMA nodes. We can also see the capacities of the L1, L2, and L3 caches. There's also going to be some output that lists the flags. This is pretty low-level information. You don't need to concern yourself with most of the content, but sometimes you'll be interested in which instruction set architecture is supported. There will be flags called AVX, AVX2, and possibly AVX512, which indicate the availability of instructions that can greatly improve the performance of some numerically intensive applications. We could also get memory information at /proc/meminfo. So if I look at this file, I could see the total amount of memory. I could see how much is active. The units are kilobytes. So if you divide this by 1024 squared, you'll get the net number of gigabytes, which in this case is going to be 256. We could also see the amount of memory, say, on a large memory node if I had been logged in there, or on a GPU node if I was connected to a GPU node. So I'm just going to finish up. We're going to look at Linux quotes very quickly. Linux provides single and double quotes. Single quotes preserve the literal value inside the quotes, and double quotes recognize the special meaning of dollar signs, single quotes, backslashes, and if you have history expansion enabled, the exclamation point. So let's look at two shell variables, or actually environment variables. I'm going to define var1 and var2. I'm going to assign them values. If I do echo, and then in single quotes, $var1 plus $var2, I'm going to get that literal string. The dollar signs are treated just like any other character. If I use double quotes, now the dollar is going to retain its special meaning, which is to access the value associated with that variable. Now we do echo in double quotes, $var1 plus $var2, and I will see the contents of this variable. Now, if your strings don't require any special characters, you can use the single and double quotes interchangeably. I find this really handy if your strings have quotes. You can also use backslash to escape characters so they don't have their special meaning, but this is a little more awkward, might make your scripts a little bit harder to read. So let's say I wanted to print out the string, "Good morning, Bob," and I have Bob in single quotes. I could have wrapped all of that in double quotes. So now single quotes are treated as single quotes within that string. Similarly, if I wanted to write out the literal string, "Good morning, Bob," with Bob double quoted, I could surround Bob with double quotes and use single quotes to contain that entire string. I could have also used backslashes to take away the special meaning of those double quotes. You can see that without the backslashes in this third echo command, I would have double quote, "Good morning," double quote, "Bob," double quote, double quote. And we're not going to get the result that we expect. I could also use the backslashes to get rid of the special meaning of a backslash or the dollar sign. So here I have echo in double quotes, $var1 plus backslash, which tells me that I want a literal backslash dollar, so I get a literal dollar sign, var2, and then backslash. And then finally, these aren't really quotes, but I'm going to lump them in there. Linux has backticks that are distinct from single and double quotes, and they capture the output of a command. So let's say I want to capture the output of the whoami command and the output of the date command. I'm going to save these in the variables me and date. So I could do echo $me, and I could see the output of the whoami command. I could do an echo $date, see the output of the date command. So I'm going to wrap up here. Just going to say that learning intermediate Linux skills will help you become a more effective user of advanced cyber infrastructure. Hopefully this tutorial provided you with the tools to customize your environment, automate tasks, construct simple workflows. And while we covered most of what you should need to know, there are many resources in a wide range of topics in case you need to go deeper. So there's a great advanced bash scripting tutorial here, and a forum at linux.org. And we also have some supplementary material. I am not going to go through this now. If you're interested in learning a little bit more about the Linux file system hierarchy standard and the difference between hard links and symbolic links, I give some examples here contrasting the two, and a wrap up with a couple of examples of when you might want to use a hard link. As I mentioned earlier, I have never found an instance where I actually needed a hard link, but you might find some cases. So with that, I am going to wrap up. I'm going to stop sharing, and I am happy to take any questions that haven't yet been answered.